Hi and welcome back to our channel. In the last video, we talked about the earliest finish time scheduling strategy and how to write its proof of correctness by induction. So right now in this video, we are going to take an actual example. And if you recall from that last video, we said that the earliest finish time strategy is greedy. It's a greedy algorithm. So in the example we're going to take right now, we're also going to use the greedy algorithm or the greedy method to solve this problem. And after solving the problem, we are also going to write its proof of correctness by induction also. So let's take the example. Let's say you are consulting for a trucking company that does a large amount of business shipping. They ship packages from New York to Boston. So let's say from New York to Boston. Yeah. The volume is high enough that they have to send a number of trucks each day between the two stations. Trucks have a fixed limit, W, on the maximum amount of weight they are allowed to carry. So each truck has a weight limit. Let's call it capital letter W. They can't carry any weight that exceeds W. Boxes arrive at the New York station one by one, and each package I has weight WI. So each package weighs WI. Okay. The trucking station is quite small, so at most one truck can be at the station at any time. Company policy requires that boxes are shipped in the order they arrive. Otherwise, a customer might get upset upon seeing a box that arrived after his make it to Boston faster. At the moment, the company is using a simple greedy algorithm for packaging. They pack boxes in the order they arrive, and whenever the next box does not fit, they send the truck on its way. But they wonder if they might be using so many trucks, and they want your opinion on whether the situation can be improved. Here is how they are thinking. Maybe one could decrease the number of trucks needed by sometimes sending off a truck that was less full, and in this way allowing the next few trucks to be better packed. So this is our question. We want to prove that for a given set of boxes with specified weights, the greedy algorithm currently in use actually minimizes the number of trucks that are needed. Your proof should follow the type of analysis we used for the job scheduling problem. It should establish the optimality of this greedy packing algorithm by identifying a measure under which it stays ahead of all other solutions. So how would you solve this problem? If you can, I would recommend you pause this video for about a minute, think about this story, think about how you would solve it, and then you continue. Okay, so input in this question, we have our input. We have I boxes weighing WIH. I remember we have a constraint, right? Constraint is that I think we should just write down this constraint here. This is our constraint. by the way. Each truck cannot weigh more than capital letter W. That's a constraint. And we want to assume, our assumption for this problem, we want to assume that no single box weighs more than capital letter W. No single box weighs more than this. Okay. And we have I boxes weighing WI each. That's our input. And we have each truck has a limit. Each truck has limits, big W. Okay. So let's talk about our strategy. Meanwhile, after we are done with this video, if you thought about a different strategy than the one we are talking about right now, I'd love to see it in the comment section. Do well to put it in the comment section, and would all look at it together. So for our strategy, since our boxes are sent out in sequential order according to arrival, we are going to use first come, first serve strategy. And that's because according to company policy, as I had told you earlier, the boxes are sent out in first come, order, because a customer wouldn't want to see a box that arrived after his own get to Boston earlier. That's the first one. And then with this strategy, we will load the boxes in their order of arrival. And when the truck reaches its maximum capacity, we stop loading the truck and send it on its way. Then the other boxes are loaded still according to their order of arrival on the next truck until that next truck reaches its maximum capacity. Then we send it on its way. And then we continue like this until we run out of boxes. So let's I like to use diagrams. So let me illustrate everything I've said so far with a diagram illustration. So let's say this is truck 1. This is let's call it truck 1. I'm going to put in boxes in truck 1 until it reaches less than or equal to big W. So I have, let's say, W3. Then this is truck 2. This is truck 2. I'm going to put in little boxes in it until, let's say I have this. This is truck 3. For truck 3, let's say I have this, and I would continue this way until I run out of small boxes. And for each truck I have, and if you remember from the story, I said that the company only has one truck in its premises at a given time. Because of space constraints, it can't contain more than one truck at a time. So this is truck 3. So I'm going to continue in this way, filling up each truck that I have until it gets to its maximum limit before I would start to fill the next truck. So my observation, what's our observation about this algorithm? The observation is that each truck takes in the maximum number of boxes before it drives off, just like I said. And at most, one truck will be on its way before we start loading the next truck. So we cannot have any box load before any box preceding it. So let's write our proof of correctness by induction. So for this proof, proof of correctness by induction. So just before we start writing the proof, all we are saying in our solution is that the company's simple algorithm is the best algorithm we can use to solve this problem, given all of the constraints. The constraints being that we cannot send off a box that arrived after a given box before it, and we cannot have more than one truck in the premises of a company at a time, and we only send out the trucks one after the other, and each truck has a weight limit of capital letter W. So considering all these constraints, the company's simple greedy algorithm, which they're already using to solve this problem, is the best algorithm that can be used to solve this problem. So let's prove that this is correct by induction. So in this proof, we are going to show that we want to show that this greedy algorithm is better than any other algorithm we can think about. The greedy algorithm, in other words, stays ahead, right? It stays ahead. So we want to prove that for a given set of boxes with specified weights, the greedy algorithm currently in use minimizes the number of trucks that are needed. That's what we want to prove here. That this greedy algorithm minimizes the number of trucks in use. That's what we want to prove here. Therefore, the greedy algorithm stays ahead of any other solution. So, just like I mentioned in the last video, the first thing we want to do is specify our definitions. So first off, let's say A subscript I for the greedy algorithm. So we want to define this as the first I boxes loaded in the trucks. Loaded in the trucks and greedy solution. In the greedy solution, then we want to define OPTI as the first I boxes loaded in the truck in the optimal solution. So here we have in the optimal solution, which is any other solution we can think about. So now we have to define our measure of goodness. So for this question, I'm going to define my measure of goodness as the number of boxes transported by each truck in the solution. So let's call this the number of boxes transported by each truck. Your measure of goodness definition must not be the same with mine, but it has to be a definition we can use to show that greedy will stay ahead. So, but for me, I'm going to say that the number of boxes transported by each truck in the solution, by each truck in the solution. So, if I say that my measure of goodness is the number of boxes transported by each truck in the solution, then my claim, which is the next part of this proof, my claim is going to be that the greedy, that is, will transport more boxes in each truck, and that will be greater than or equals. I hope this makes sense. In this case, because my measure of goodness is the number of boxes transported by each truck, and in this greedy algorithm, I'm going to fill each truck with boxes until it gets to the limit. it means that my claim is going to be that the number of boxes for the greedy algorithm transported in each truck will be greater. Now, let's say that I define my measure of goodness as the number of trucks used for transporting all boxes. That's also a valid measure of goodness. Supposing I use another measure of goodness, let's say I say my measure of goodness is the number of trucks used in transporting all boxes. If that's the case, my claim is going to be that with the greedy algorithm, I'll use lesser number of trucks. So now I have less than this. Let me say it again. Supposing I define my measure of goodness as the number of trucks used for transporting all boxes, this would be my claim. I'm going to claim that the number of trucks used for the greedy is less than the total number of trucks used for any other optimal solution. Okay, I hope that makes sense. So let's get back to this. So using this as my claim, what this means is that the number of boxes, like I said, transported by the greedy is greater than the number of boxes transported by each truck in any other solution. So to illustrate this claim, I love to use illustrations. To illustrate this claim, let's call this the OPT. So for this is a truck. This truck might have just this. The next truck might have this. The next truck might have this. That way until we get to the last truck. But for our greedy, the first truck will have the most number of boxes. The next truck the same way. You see that for the greedy, we have more boxes in each truck, just like that, until at some point here we'll have this. Okay, so that's each box here represent a truck, each rectangle here represent a truck. Okay, so having said that, let's move ahead. So now let's consider the base case. Our base case where I is equals 1. So when we have one box, the optimal algorithm will use one truck, right? We'll use one truck, and the greedy would also use one truck. So our claim holds that this is greater than or equals this. This still holds, it's true. So let's consider the induction case. So by induction now, let's assume that this. Okay, so if this is our assumption by induction, let's illustrate this. By illustration 2, we would have the truck 1. For OPT, we have truck 1. Truck 1 did not maximize the total weight of the truck. We have truck 2 and all the way to truck I minus 1. But for greedy, we have truck 1 having all these boxes, truck 2 having all these boxes, and then somewhere here we have this truck having this box. So that means we have the number of boxes in each truck in the greedy, right, is still greater than the number of truck boxes in each truck in any other optimal algorithm. So because the optimal algorithm does not fill the truck to capacity W to the big capacity W, right, it transports fewer boxes per truck as illustrated above here, and that means our OPT takes more number of trucks. So this conclusion is very important. We have illustrated our claim and it's correct. So we have to come to that conclusion that since our OPT, does not fill our truck to the capacity, it doesn't maximize our capacity W, right? Because it doesn't do that, OPT is going to take more number of trucks to transport any number of boxes. Unlike the greedy algorithm, which transports more boxes in each truck, filling it to its capacity W. Therefore, we can say that the greedy algorithm currently in use by the company minimizes the number of trucks that are needed. So that's how you would solve that problem. I hope you really enjoyed this video. If you did, kindly remember to subscribe, like, comment, share with your friends, and I'll see you on the next one.